Chattopadhyay, Professor in the Department of Mechanical Engineering at Himadri University, Kolkata. So, Professor Chattopadhyay is a very experienced professor in the field of thermodynamics and heat transfer and fluid dynamics area. So, I will request Professor Chattopadhyay to take the step.
So, from the morning we are hearing a lot of interesting lectures with a lot of rigors and figures. So, I will be rather on the populist side, but it touches the periphery of the main subject. But again, we have to see the connections of the fundamentals, as in the earlier session also that we were discussing about how physics is dictating things. So, so this previous,
So, open it.
right, thank you. Yeah. So this is a picture. Tomorrow we have a visit to Eiffel Tower, and this is a picture just in the passing. I am just showing it. Henri Rousseau, a French artist, and you can see the Eiffel Tower on reverse side. So years back. So and now this place has changed. So I have a copy of this image at my home, and so I thought I include it so that we can appreciate. Okay, so
Open it. Click.
right. Again, response is slow.
Yeah.
Yeah. So this saying that all sciences, either physics or stand collecting, so that is attributed to Rutherford. It's not very clear that whether he really said so, but if we look into the subjects of physics, chemistry and biology, so biology is basically applied chemistry. We look into the reactions, that how things are performing, and now from biology if you go to chemistry actually all the reactions that arises out of the interaction at the molecular and still fundamental particle levels. So basically this way physics, chemistry, biology are connected down the line. But at the same times, in this century and as we are progressing in time, people are feeling that more problems are lying in the biology, because ultimately everything is for human well-being and humans are involved. So for example, say Venkat Ramakrishnan, who got Nobel Prize on his research on ribosome. So like he was a biochemist, he was basically a chemist by training, but when he was trying to find an interesting problem, he found that most of the problems in chemistry are solved. But life is offering a lot of complexities which are not really solved and will take decades and centuries to solve. And so therefore, physics may be the driving factor in one side, but on the other side, we are finding more problems in biology, and we are trying to, and it has become an interdisciplinary area where all fields are working together to go into this. So yeah, sorry. So this picture, actually it is from a book of McFadden and Al-Khalili, Life on the Edge, a popular science book. So we can see that how things are connected. Like for example, flight of a plane, how a vehicle moves, or even sports and all the events, day-to-day life events, we can very easily describe by Newtonian mechanics, the force and the movement of things. Now, at the microscopic level, where there are a lot of particles are involved, thermodynamical laws govern the systems. And finally, quantum mechanics. Because again, as we are discussing that ultimately everything is the interplay of particles, and where the physical laws of the this case are different, and where we have to understand things in a manner which was described by Schrödinger, and then subsequent developments where the conventional thinking fails. So down the line, if you have to analyze things, you have to go to the quantum mechanics level, and in between thermodynamics has a role to play, which gives us a lot of insight and understandings and idea about developing things. So for example, like a lot of properties which we are discussing, like pressure, temperature, and all these things which actually dictate the system behavior, basically are outcome of the interplay at microscopic level. So however, without going into the detail of the microscopic description, we can talk on the macroscopic level, and macroscopic thermodynamics has developed certain laws which are applicable to universe as a whole, and to the down the line to physical systems and processes. So, like this is said that that physicist Uwe Lode, he has said about the power of thermodynamics that you see that it is a remarkable illustration of the ranging power of the human intellect. That a principle dictated for puffy steam, clumsy steam engine. So where there are a lot of leaks and pollution and all these things. But where people studied the work and heat interaction, so laws are developed there which should apply to the whole world and possibly even hold to the cosmic universe. So the thermodynamical laws helps us to studies, for example, energy conversion devices, the chemical conversion and reactions, which is applicable to biological processes as well. See, astrophysics, the living systems, and also it dictates the directions. Like sometimes the mathematical formulation or the formalism of physics, formalism of physics without the thermodynamics do not help to understand the direction. So it looks like to be reversible, yeah, but in a thermodynamic aspect, there is an arrow of time and which dictates the directions of the processes. So then interestingly, the first law of thermodynamics, which is talk of that we feed energy and we convert the energy to something useful, and for that we define a thermodynamical efficiency. Like the cow eats the hay and it produces milk, and we want that we get maximum benefit. So this is what is we can call the first law efficiency of a thermodynamical system. So which is applicable to say automobile engines, to power plants, and we can think of human being as a heat engine. Even the tissues and cells, they are also sort of heat engines which consume energy and produces some useful energy in the form of work. So we have the first law efficiency defined as the useful work to the heat input. And if you look at the values, say typically engineering science, the value we deal with is 30-40%. So for power plants, automobile, this sort of values. And photosynthesis is very interesting. We get an efficiency of 2%. So looks like nature is very inefficient. But the thing is, nature has so much supply of energy. There is so much abundance of energy. So it does not need to evolve a system which has to be efficient in that manner. So, like it is a French physicist, engineer, Carnot, who has given the values of what can be the maximum efficiency, which govern the first law efficiency. Is something like mechanics of fire. So I cannot really read it, but this. And also in this context, that from thermodynamics also comes the concept of stability and equilibrium. So basically, in living systems and living reactions, they are mostly in the non-equilibrium zone, and this figure helps us to appreciate that, like for example, an object held at a height will fall, and here it is metastable. So at a certain zone, some kind of perturbation will not disturb it, but some little more of perturbation, it will fall into the target. And is, for example, here where it has the lowest energy, so it has become stable. So this is applicable to different systems. And for example, like we are today discussing of the metastasis and cancer and all these things. So here also again, the system is seeking for an equilibrium which can be explained and understood from the thermodynamics perspective. So for example, see, in chemical processes, the energy currency that is used gives free energy. So for example, like this body will fall to minimize the potential energy, and for a chemical systems, the enthalpy and the environmental temperature and entropy, so it wants to minimize the value of Gibbs free energy. So I can skip this thing, but the second law of energy is very important because it defines the feasibility of a process or the direction of possible energy conversion. And we come to the concept of entropy. So this is quite well known. So without going into the detail, we can summarize this as in the following manner, that there is always a price for conversion. So none shall give you a rate of 100%. So always there will be some loss and some dissipation involved. And the natural direction is in the direction of entropy increase. As we say that the entropy of the isolated system always increases. And all types of energy are not equal because it is not only the quantity of energy, but the state of the energy in terms of entropy that is important. So entropy is thought to be a belief of the order or disorder of the system. It is depicted in the cartoon. So and again, to understand the biological thermodynamics, the term information entropy becomes important. Shannon's value of entropy, which depends on the probability and given in this manner. So when we see logarithm of px, so when we know something for certainty, then it becomes all information are available. So these functions become 0, and particularly these are important for biological systems, and like because say cell and tissues are thermodynamical open systems. So the speciality of living cells are they are capable of organization and cell replication. And we see the standard thermodynamic analysis, we are more concerned about, or we are rather focused on mass and energy which transits the boundary, crosses the boundary. Now for a biological system, the mass energy, and we have to give some special emphasis on information, because through the genomics that controls the systems and its evolution. So the exchange of mass, energy and information that control the behavior of the system. So it is said that life is an extraordinary challenge that defy entropy. So entropy is sort of thought of disorder and most probabilistic state, but the self-organization in the living systems, they are seem to be going in a contrary manner. So a trigger of abnormality for any of them, that mass, energy and information, this trigger of abnormality in any form can lead to derivation from a normal biological function. So that is, for example, things in a metastable state, some kind of perturbation can change to a totally different zone it can live. So, for example, development of instability or metastability. Like you can this metastable system, I can give an example. Say safety matches. So a match stick is very stable; it does not burn. But you give certain pressure, so it will ignite. So you see that the level of perturbation is little more, then it totally transforms itself. So otherwise it looks to be a stable system, but that level of pressure brings it into totally a different regime. So recently researchers are doing this thing, that trigger of abnormality that can lead to instability, which has a role in the development of tumors, and it can trigger tumorigenesis and also by increasing what is called gene network entropy. So, like say Lutege, this 2000 recently told that genes and genomes are like a grand piano. Music emerges when it is played. So it is being described as what is called the emergence phenomena. So 2 plus 2 is 4, but like when there are say water molecule, two more water molecules are mixing together and they are forming water droplet. Now they have behavior which is much different from a single water molecule. Similarly, say the proteins and genes, they are interacting to form sort of emergence, so which is giving a totally complex phenomena which is very difficult to analyze. So from thermodynamic perspective, if you talk about to the particular this domain, it is found that cancerous tissues have higher entropy generated locally, the volume and temperature. So local temperature of the tissues are higher, they seek increasing the volume, and there is locally entropy generation. So modeling the evolution of the thermodynamic parameters has a scope in cancer research. Recently, a lot of papers are coming into that, and this it shows that some external field like electric or ultrasonic, they can, like entropy generation. So it is, entropy is defined by del Q by T, but it is not only the heat, but other factors can produce entropy, like even friction and chemical gradient. So similarly, the external field like electrical and ultrasonic, they can alter the direction of entropy flow. So for example, 2006 studies, it shows that quantified that application of electric field that can lead to higher entropy generation. So like as I was telling, that several factors which can cause entropy generation are like temperature gradient, chemical potential gradient, particularly in a cell environment, viscous dissipation, chemical affinity, and of course others force field. So like here some values are given, like thermal part. So normal cell is residing in the same cellular environment, so naturally there is no temperature gradient. But a cancerous cell, it will have a higher value of temperature, so there is entropy generation. So now if you look into this thing, diffusion, affinity, viscous dissipation and force field, you can see that in all the cases, I mean about not for the force field, but this diffusion, affinity and dissipation, all the case the entropy generation in cancer cells are higher by certain factors. Now, suppose a square wave electric pulse, its effect when it is calculated, it is find that the reverse is happening. So, for the entropy generation by a force field for a normal cell is higher than that for cancerous cell. So that is why application of these fields, they are effective tools. Means that can be linked or correlated as an effective tool for treating this sort of tumors. So these are formulation. Let us not go into the details. thermal gradient and all this thing, but chemical reaction. So chemical reaction, one important thing is like if you look calculate the second law efficiency, these chemical reactions are important. So this can be just simple pen and paper calculations, but you can find out the chemical efficiency. So for normal cells, 1 mole glucose can produce 31 ATPs, whereas for cancerous cells, we will have less number of ATPs. So you can have the entropy generation correspondingly, which depends on the oxidation rate of glucose. So then the viscous dissipation, as we have already morning we have discussed, that it depends on the velocity gradient. It has a role on the system. So force field, actually the form of the cells as such that you can see in the second formula for entropy generation, that it depends on the root n. So for cancerous cell, so I have not really understood that why it is like this, because the cells are organized in a little different manner, where n is the number of dipoles in a cell. So if you look into the formula for normal cells and cancerous cells due to electric field, there is it is proportional to root n for cancerous cells, because in a way they organize that number of dipoles formed in a tumor is less. So this leads to the fact that there is less entropy generation for cancerous cells when electric field is applied. Now the so the second law efficiency can be calculated in this manner, that energy stored in ATP and energy produced in 1 mole glucose oxidation. So again you can see that healthy and cancerous cell, the chemical efficiency is very much falling for cancerous cell. So from 50 to 3%. So it has lost log efficiency, and they generate approximately twice an entropy for oxidation per mole of glucose compared to normal cells. So, like many people consider Bejan's constructal law as a fundamental contribution to thermodynamics. So, Bejan states that a finite size flow system to persist in time. So, as a system evolves, it finds the route where it can maximize the flow. So, this is again a sort of extension of second law, and it has found applications in many applications, including the cancerous areas. So just to understand this constructal law, just I am giving an interesting aspect. Like if you look at the design of monitors, so earlier, if you remember years back, you used to have square monitor, and now the monitors within the screens in the theaters, cinema halls, they are longer. So what is the time to scan an image? You see, this is the length. So length by the scanning speed. So this length by scanning speed, and this width height by the horizontal scanning speed and vertical scanning speed. So our horizontal scanning speed is higher. We can scan quite fast than in this direction. So if you optimize that, so it points to the direction that basically we just thought that if square is our choice design, but the optimization which evolved in time led to a longer in horizontal dimension, where we get lower T to scan certain area. So this is just to show that how this constructal law can be used. So this constructal law can help explain and predict the growth of tumors where area and volumes are involved. So like cell surface modification certainly has therapeutic potential, and so certain lump analysis are being carried out. So it's not that always they are giving very good result. So for example, this sort of this what is called lump analysis, like if you are boiling a potato and or say I have a steel sphere and a potato. So how the temperature field inside, how it will behave, it depends on these parameters: the density, the heat capacity, and the heat transfer coefficient around it. So this tumor has a inside temperature T tumor and the outside is T0. So the heat transfer coefficient, area, then initial temperature drop across this tumor and outside, then it behaves exponentially. It is basic heat transfer, this thing. So now, therefore, from this relationship, this tau is a time scale. So it depends on the density, the volume and area ratio, and the specific heat of this thing. So, for example, when t equal to 3 tau, this equation comes to a state that when delta t is reasonably small, there is not much heat transfer. So, if you like electric membrane potential, so this like gives free energy. So this membrane potential is given by H minus Ts. So this Ts can be changed to Q dot tau, where Q dot is instantaneous heat transfer rate and tau is some time scale, like which depends on V by C, and then the gradient of this pH value. So where this R is universal gas constant and F is a Faraday's constant. So this is electric membrane potential, and for cancerous cell this value is 10 millivolt, and for normal cell minus 70 millivolt. So because of if you take the all other things same, but we focus on the tau value, which is dependent on the volume and area of that cell, we can find such a relationship that tau normal and cancerous and is given by, so 2 times of almost 13/7, that is almost 2 times the volume and area of normal. However, normally we know that tumors grow, so volume grows for cancerous cell, but however the volume by area still grows faster, and area by volume. So tumors have more area by volume. So this result is not really correct. So therefore, certain factors which you take equal, there is also some problem. But this is just to show that you can extend this sort of analysis of lump system to understand the evolution of the geometrical parameters. So, with some of the recent studies showing that thermodynamic model can be used to find out a critical volume which reaching invasive stage can be predicted, which depends on the excess temperature of the tumor over the environment. So, like we have from this type of thermodynamical model and this tau, which we discussed already, the models have been developed for this mice models, where this is the tumor, these values are given, like this is the tumor patient, this is non-tumor. So these models were validated, and entropy generation was found to correlate better with metastasis rather than only temperature. So entropy generation was a better indicator. So now chaos theory or nonlinear theory also being applied to lot of fields. So again here certain applications of are found describing the growth of tumors and cancers. So like M is the multiplication and repair, and F is the biological function. So this is sort of a general nature of things. So where this is dictated more by entropy generation, and here dictated by chaos, and this is the healthy zone. And now this thing, or from organelle to cell to tissue level, there are connections which can be expressed by this nonlinear models described by chaos theory. So therefore, again, as a thermodynamic indicator, like temperature can be used as a control tool. Similarly, from the chaos theory, that chaos has a connection to development, like the growth and means undeterred growth, all these things. So there is a this chaos can be studied to help understand and to tackle the problems. So there are, for example, a recent paper in drug discovery, so which is telling that this can be the possible tools of chaos control, like anti-angiogenesis, where through proliferation of blood vessel using drug targeting therapy, through differentiation, for example, by stem cell. So these are basically these are known things, but basically you can see them from the nonlinear theory or chaos theory angle. That how, because as we know that chaos theory tells that initial disturbance initial condition or initial slight change in initial condition can lead to a totally different result. So therefore, this certain factors can lead to a very different state, which can be desired or undesired. So that can, so they are like differentiation, then pro-senescence by stimulation using senescent cells, like adaptive therapy. So for example, the therapies like certain chemotherapy, like lot of normal cells also try. So adaptive therapy will against the fixed treatment protocol, it will be continuously modulating the treatment to attain higher fraction of healthy cells. So and circadian rhythm, so like melatonin has protective effect. So again, if you can tune the treatment with or in circadian rhythm, the rhythm that can again control the proliferation of cells. So, and also, for example, my studies were related to thermodynamics, but as I said that there is a quantum connection. So recent paper like quantum biology, so like through microwave technology, which is called passive microwave radiometry. They are the sort of new horizon which is opening. So to conclude, so biological thermodynamics shows certain interesting angles on the subject. So as the cells interact mechanically, electrically, chemically, and through processing of informations, and where they are open systems, so thermodynamic understanding can be helpful to study the growth and eventual prediction of the behavior. And particularly interest is the evolution and exchange of entropy, which can be controlled by applying fields and flow control and chaos control. So through nonlinear theory has a potential route to win over the deadly disease. So thank you for your kind attention.
Any question? First,
so thank you very much. Really driving and interesting. I have two questions. The first one is about this, polarization in cells with electric field, and you said that normal cells is proportional to n. Just wanted to.
But that I already admitted that I myself could not understand. But there is a difference in the structure of the.
But so this is experimental or is theoretical prediction?
Theoretical prediction.
Okay. But on what is that based? I mean, so how do
they,
you get this route?
Because they actually depend on the certain states. They are dividing the cells in certain states. So that is for a living thing that is n, whether for the other thing it becomes a proper n.
Okay. Okay, so maybe I give you this one, take notes as a question.
Yeah, so I had two short questions. First question, again related to that part where you're talking about use of electric field and ultrasound as well. First part of the question is that specifically ultrasound, these are highly penetrative, and while it's certainly maybe feasible in an isolated tumor microenvironment, when we're talking in a real case scenario, won't it just affect or harm the other healthy cells? That is the first question. And second question is that the whole problem which I see with cancer therapies is that cancer adapts. And while certainly it may be true that the entropy of cancer cells is higher than that of normal cells and the chemical efficiency is lower, won't they just adapt to it, especially the stem cells, when they are treated on maybe with electric field or ultrasound? Maybe they will adapt to those niches, and eventually it will become into a state where you cannot apply those therapies. It will develop resistance to that. So these are my two questions.
Yeah, so actually this cancer, this cannot be readily answered because we have to actually really watch the way it is evolving and then how the problems are tackled. That is again interesting, and that has to be really watched. So, and what you told that in therapies are always this sort of problem. In chemotherapy also, that all other issues they go on dying and all this thing. So here particularly the targeting is like drug targeting, and similarly the field targeting also, that technology, that development is again for bioengineering and related field.
But tumors are they're embedded within the body part, and then like ultrasound, these are penetrative. It will penetrate every form of cell which is there. That's why ultrasound is used for USG and all that, ultrasonography. The problem which is coming up is that if that's embedded within a tumor, then you cannot just extract it or even tune the frequency. That will inevitably harm the other cells.
Technology, like for example, like removal of stone. What is that called? Lithoscopy or something like. So now this teeny teeny pipe can go and do the
Isolate the tumor
so
out.
similarly, such things, such technologies may be possible. Once you know the theory, then adapting to technology that can come and follow that.
Right. Thank you.
I have one short question. So just in the other question, it was about fractal dimension. Also there, it's something that is known experimentally or something.
Yeah, the fractal dimension, yes. The fractal dimension are experimentally measured.
But how? What?
So that detail I have not gone into, but I can give you the paper.
Please, yeah.
What is the origin between the membrane potential between tumor cells and normal cells? Because I see there is huge difference, 10
Huge difference,
millivolts
yeah.
and 17 millivolts. So
But they are experimental values. So why it is like that?
Yeah, this is
The properties
my
are totally changed. So the change properties like temperature, only tumors have high temperatures. Similarly, the chemical potential, it has been recorded that it is high. But why? That is
so maybe some biologists, colleague biologists can answer something. Okay, thank you very much.
Thank you.